things we're going to be doing today. Some of them we have done before, but I'm just putting them in, and most of them you haven't. And it's all to do with probability. So let's look at types of probability. Well, you've got ones that you could essentially call them personal probabilities. And these don't have any scientific background. These are judgment calls that people make. So you may have a friend and you might talk to them, talk to someone else about them, and you might say something like, do you know, John, there's a 50% chance that whatever he tells you is a lie. Right, that's just based on your gut feeling. Oh, John, there's a 99% chance that whatever he tells you is just a pack of lies. Right. What you're doing there is you're putting your own personal opinion on the likelihood that if he told you some fact that it was actually true or it was a lie. And you might say, well, you've based that on experience, but it's very unscientific. So we don't use those much. Then we have probabilities that you get from relative frequencies. An example of that might be that you collected data on married couples and you found out how many children they had, and you, to make my life simple, let's suppose the biggest answer was 4. And in this sample, 32 of them, that's 14, 17, 12, and 5. That was the data we got. So should I actually find the total now? And that's 40, 46, 56, 63, 73, 75, 80. That was lucky. Right. And from this table, you can answer probabilities like, what's the probability I just randomly choose a married couple and that they have one child in their family? And the answer would be 14 out of 80, which you could simplify down to 7/40ths, or turn it into a decimal, or for that matter, you could turn it into percentage. So relative frequencies are very common. Recording in progress. Okay, so the very common things, you can imagine how you would you could collect your data. They are always based on data that has been collected either by you or by someone else. And the larger the total, the more confident you should be on any probabilities that you get from it. So since this is a very small sample of 80, when I take it with a pinch of salt, that the probability I just choose somebody at random and they have one child in their family of 7/40ths is really just an approximation to what it probably is. Whereas if I did, I don't know, 80,000 people, I'd be really comfortable that the answer was darn close to that. And then we've seen this one before, but kind of putting it in its package. Theoretical probabilities. Now, these are ones where you don't actually physically collect data at all. You can do it through logic. And typically the way you might do that is, I like cards because they're the best for these. If I went and said to you from a card, what's the probability that I pick one card? Everything we're doing right now is kind of to do with one of anything. I get one card and it's an ace. Well, I know that there's only 52 cards in a deck and that 4 of those are aces, and that simplifies down to 1/13, which is about 7.5% chance of happening. Now, I never actually got a deck of cards and picked one out and said, oh, that was a king. Then I'd done it 2,000 times or 2 million times and put on the top how many of those 2 million times were aces. And on the bottom, I put 2 million, then I simplified it. That wasn't done that way. That was simply just done by knowing all the things that could happen, 52, and on the top, the number of ways this particular event, in this case, aces, could happen. And theoretical probabilities are by far the most accurate. Right. Relative frequencies are accurate for large sample sizes that kind of hit and miss, you know, the smaller the samples get. And personal probabilities, what you think the probability of something going to happen is, are by far the weakest and not accurate at all. Any questions about that, or does most of that kind of make sense? We good? Okay, I'm just going to close, not close the window. I'm going to change the window a little bit. If that's the right word. Yeah, because I cannot see. Darn it, I've lost it. That's what happens when you move windows around. I cannot see all the people that have their video on, and it helps. So if you just give me a few seconds to just rearrange it. Oh, well, that's kind of it. Can I go down here? There, that's better. So, 3 types of probability. We've kind of touched on all of them. In no particular order, I just wrote these down as they come into my head. Let's look at what are called mutually exclusive events. Kind of fancy word, but essentially you have an event A. So event A might be red cards. And event B could be clubs. This is an example of mutually exclusive events. What that means is the things that make up event A, in this case red cards, and the thing that makes up event B, which in this case is clubs, they share nothing in common. So mutually exclusive events share nothing in common. So for instance, clubs and hearts are mutually exclusive events. Males and females, yeah, depends how you want to define it, are mutually exclusive events. God, it's hard to think of some off the top of my head. It's probably too early in the morning. My brain, normally I'm pretty good at. Can anybody chuck in 2 mutually exclusive events while I think of some more myself? Too early in the morning for everyone? Come on. Think of 2 things that share nothing in common. They have to have a common theme, like they're both picked from the same pool, but they pick different things from that same pool. Oh, how about this one? Junior high school students and sophomore high school students. Would you agree they're mutually exclusive? I don't think you're allowed to be both at the same time. There, that would be an example. People who were born in Scotland and presidents of America. You can't be a president unless you were born in America, I believe. Are we cool with that? I'll probably find 10 other examples, but that'll be too late because we'll have passed it. So, 2 things are mutually exclusive events when they share nothing in common. The next one in the list is, I say, in no particular order, is independent events. And this is what they look like. 2 events are independent when the outcome of one event has no effect on the outcome. Of the other event. So you've got 2 events, call them A and B, and they're said to be independent if event A happens, or if you know that event A has happened, it has no effect on event B. So let's pick a really silly thing. Event A is that it rains in Bremerton. And event B is I throw a coin in the air and it ends up being a head. Would you agree that if it rains in Bremerton or if it doesn't rain in Bremerton, it has no effect on me throwing a coin and getting a head or getting a tail? You see, those two things are quite different. Right. Now, you can actually have two events that are the opposite of independent, and they are called not independent, which I think is a horrible name. I prefer the word dependent, which you'll find in a lot of textbooks, but not in this one. And two events are not independent when what happens in event A affects what's going to happen in event B. So I'll give you an example. Suppose A was I got a king. And B was the event that I got a face card. Would you agree that if I picked a card out of a deck and it was a king, the chances that I now have a face card are pretty much 100%? Agreed? But in a way, they're kind of in step lock. Do it the other way about. Suppose I did event B. Suppose I picked a card out of a deck and it was a face card. What's the probability that that card is a king?
100%.
Yeah, well, let's look at it. Let's do the numbers. The probability A is of getting a king. Whoops. So it's the probability of getting a king. And we know that's 4 out of 52. So isn't the chance of getting a king 113? Right. Now, what's the probability, and this is how you write it, of getting a king, given that you already know that it's a face card, which is what event B was? Well, since I know it's a face card, how many in the deck are face cards? 3, 6, 9, there's 12 of them. And 4 of those are kings. Do you see it has a one? It had a direct effect on the probabilities, right? They interacted with each other and they made the difference. So those are examples of independent, or in this case, not dependent. Let's look at some more independent events. Event A is it snows, and it snows today, right? And event B is I win the lottery. They would be pretty independent of each other. Want a dependent one? Event A is it snows today, and event B is it's cold today. Well, if it snows, isn't there a pretty good chance it's going to be cold? Not guaranteed. Well, the other way around, it's not guaranteed. Couldn't it be cold and not snow? If it snows, it will be cold. Right. Are we cool with independent and not dependent? Independent? You know, we're going to see questions on those as well. Next one in our list, as I said, there's no particular reason or rhyme to them, is D, which are called complementary events. The complementary events are very similar to mutually exclusive, but not exactly the same. Two events are called complementary. CE for short. If column A and B right now, I'm going to change the name. I'm trying to think how you phrase this one. Well, I'll give you an example. That's probably the easiest. A is I roll a dice and I get odd numbers. The complement of A, which is actually written down as A with a big C next to it, I'm just calling it B right now, is the other event. That's the opposite of A. So it's the opposite event from A. So if A is getting odd numbers, wouldn't the complement event be getting even numbers? So suppose event A was Monday, wouldn't the complement of A be the other days of the week? Like Tuesday, Wednesday, all the other ones. Suppose A was, it snowed. Wouldn't the complement of A is, it didn't snow. If A is, it's a male, B would be a female. If A is being alive, then B would be dead, right? So the complement of A is the event made up of the opposite of whatever is in A. Does that kind of make sense? Try to think if I phrase it clearly. But two events are complementary if they one A and the other one is everything that's not in A, right? Now, there is a property that is sometimes used, and the probability of A plus the probability of the complement of A. So if you find these two probabilities, they always add up to the same number. What number would they add up to? What do you think? All the things that could happen is in A, plus all the things that are not happening in A. You put those together.
0.
Go the other extreme. 1. Let's try one. Let's do the cards. A is you get hearts, then won't the complement of A be the diamonds, spades, and the clubs, right? Now the probability of getting a heart, that's what A is 4 out, is 13 out of 52, which is a quarter. Now, probability of getting the complement of A, well, it's all these cards, and that adds up to 39 of them out of 52, which is 3/4. And what do you get when you add them? You always get 1. Okay, I'll show you how you could use that. Let's do one with 2 dice. You know, there's some games that you roll the dice, you know, you roll a pair of dice. And just to make this interesting or a little bit more clear, for some reason, one of my dice is blue and the other is red in color. If you wrote down all the different things that can happen when you roll 2 dice, there are actually 36 things that can happen. Couldn't you get a 1 and a 2, a 1 and a 7, a 3 and a 5, a 6 and a 2? And you could also get a 2 and a 6, which counts different because of colors. So there are, in fact, 6 times 6, 36 different ways, different combinations. Combinations. Of 2 dice. And let's have event A being, you get a double. Then the probability of A is 36 things can happen. Right, if you roll 2 dice, how many ways can you get a double 1, a double 2, a double 5? How many of those are there altogether? How many doubles can you get?
6.
Right, double 1, double 2, double 3, and that simplifies down to a sixth. Now, would you agree finding this probability is not too difficult because there's not that many ways to get a double? But suppose I went and said to you, what's the probability of not getting a double? Now, you could simply just write down and count as you're writing them down all the different ways that not getting a double. So that would be like getting a 5 and a 7, a 5 and a 6, right? Or a 1 and a 3, right? And would you agree they're a lot harder to count and there's a lot more of them? Great. You could do it. If you did, there would be 30 of them. But if someone gave me this question, find the probability of not getting a double, what I would actually do is find this guy. And I know the guy that I want is 1, take away that guy. And wouldn't that be a simpler calculation? Sometimes it's easier to count the things that you're not interested in, right? The complement, and then just take it away from 1 to get the probability of what you are interested in, right? Does that kind of make sense? So that's pretty much the use of complementary. Let's do E now. And E is called conditional probabilities. A conditional probability is one that looks like this. Suppose I ask you to find the probability that you pick a card out the deck and that it's a king. Now, that's not conditional probability. That's just a normal probability. We'll call that guy A, like that. If I ask you to find the probability that you get a king, given that you know the king is a face card. Right? So you read this out as the probability of getting the king. That vertical line represents the word given, in this case, that you had the face card. So I know the beginning, there are 52 cards in a deck. But if somebody says to you, I know it's a face card, right? Just before the guy turned it over, I get a little bit of a glimpse. Couldn't really tell much, but I did know it was definitely a face card. When you do the top probability, there are 52 cards, 4 of which are kings. The answer is 1/13. If you do the probability of a king given it's a face card, we've done this one before. If you do face cards, there are 12. And out of those 12 face cards, 4 of them are that. So there is a conditional probability calculation. Now, I used them earlier to prove, to show you that dependent and independent and so on. But that's essentially what a conditional probability is. People who do gambling for a profession or they just want to be good at it have to use conditional probabilities all the time. If you're playing poker and you've got certain cards and other people are likely to have other cards, isn't your chance of getting an ace better or worse depending on the likelihood that the people you're playing against has got an ace, right? If you know that there's a good chance that that person against you's got at least one ace, isn't your chances of getting an ace to win going to be reduced? Those are conditional probabilities. A lot of things that happen in the weather are conditional probabilities. Do you know the probability that it rains tomorrow, given that it's raining today, is different, right, than the probability it's going to rain today? Because when it rains, you very often get 2 or 3 days of rain. That's just the way the weather works, right? So it's a bigger chance of happening. Now, here is a test for independence. Right, so we're back up to C. Two events are independent. So that's events A and B. If the probability of A given B is equal to the same thing as the probability of A. So what isn't that really saying? The probability of A given that you know B has happened is the same probability that it was all the time. In other words, that piece of information, the B bit, has no effect on the probability. And that means they are independent. And the equivalent of that is, if this probability is not equal to that one, then A and B are not independent. Let me try and look at independent events that you might not think are independent. Because people think independent means the two events are totally different events, right? One's rain and the other's throwing a coin. That is true, but there are other ones. So here is event A, and that is you get a king. And event B is that it was a red card. And I'm going to show you that those two events are independent. What that means is the probability of getting a king is not affected by knowing that the card was red. Let's see if that works. The probability then of A given B is the probability that you get a king given that it was a red card. Well, since I know it's a red card, there are 26 of those. Of those 26 red cards, how many of them are kings? So imagine you get a deck of cards, 26 red cards, that's all you can look at. How many of those 26 are kings?
2.
2. And so the probability of this event is 1/13. Right? So this is the probability that you get a king, given it's a red card. Now let's just find the straight probability, right? That one, which is just the probability that you pick a card and it's a king. Since there are no other restrictions, that means it could be any one of 52 cards. And there are 4 kings. And that simplifies down to 1/13. Do you see that these are equal to each other? And that means that these two events are independent. So you see that you can be 2 events in the same event, right? Picking a card from the same deck, right? 2 things from that one world, and yet they can be independent. Let's pick 2 events from a card deck that are dependent. So A is a black card. And the event that you're told that's already happened is that it was a red card. So this is going to be a pretty silly one. Probability of getting a black card is 26 out of 52, half the time. Probability that you pick a black card, given that you already know that it's a red card. Well, there are 26 red cards. None of them are black ones. You see, these two probabilities are not equal, and that makes these two events not independent. Are black cards and red cards mutually exclusive? Are black cards and red cards, are those two events mutually exclusive? I'm getting old here.
Yeah.
Older.
Yes, they're mutually exclusive.
They are, yeah. Wasn't meant to be a trick question, right? They are. Would you agree if you're a black card, you can't be a red card? And if you're a red card, you're not allowed to be a black card. That's what mutually exclusive is, right? Are A and B complementary events? So A is black cards, are red cards, all the things that aren't black cards in a deck of 52. Yeah. So what you've got here are these two events can be described in different ways. I could say that events A and B are not independent. I could say that A and B are mutually exclusive. I could say A and B are complementary. So those three things describe different attributes that two events could have. And that takes us to our last one. And these are the A, and they should do it in capitals, I forgot. Well, they actually did. They're the A and B probabilities. So if I say to you, what's the probability that it's a king and a queen? This is going to be the easiest one. Now, this is I know it's a word and, but you got to be careful here because the statistics and might not mean what you think it means, right? When you use and, you are really saying this. It's both things. So, is there any card in a deck of 52 that is a king and a queen at the same time? No. So the probability of that being true is 0. What about the probability of being a king and a red card? Now, if I was phrasing that a little bit differently, wouldn't I just say red kings? So you see the word and really means both things are true, right? Both things are happening. So we're talking about red kings. Out of a deck of 52 then, would you agree that there's only 2 red kings? And that is this one. I do another one. Let's do dice. What's the probability that you get a dice that's prime number and it's even? So out of the 6 things that can happen when you roll a dice, how many of them are even prime numbers? How many are both things? I guess you have to remember what a prime number is, but there is one of them at least. Maybe more, maybe not. Yeah. Which one is the only one that's a prime number and happens to be even?
It's 2, I think.
It is the 2. So that's how you calculate ands. It's what's the probability of both things happening? Because, you know, in the English language, couldn't and mean you get the first one and then you add up the second one, like and means add, right? That's not what and means in our world. Now here's the second one of these. There's 2 of them, and it's the or. And the or one has a very special meaning as well. In statistics, the or means A can happen, or B can happen, or both are allowed to happen. So, what's the probability that you get a king or a queen. Now, when it was an and, the answer was 0, but now things are different. You could get a king, right? Or you could get a queen. Would you agree 4 kings, 4 queens, 8 things now? And that guy, 13, 2 13s. And now I'm going to catch you. This is a trick question. How many cards are there that are a king or a red card? Now, I'm warning you, be careful. Now, not and. If it was and, it would be 2. Or, right, it could be kings, or it could be reds, right?
26.
26. Okay. So,
8, isn't it?
well, let's find out. Would you agree that there are 4 kings? You'll agree on that. How many red cards are there in a deck?
26.
26. Wait a minute. Haven't I double dipped here? Haven't I counted some cards twice? How many cards have I counted twice here?
The 2 red kings.
So shouldn't I take that away just to get the total correct? And I can't remember who said it, but they said 28, didn't they?
Yeah, I said 28.
Then there you go. You got it. So the or is a little bit weird, isn't it? Because a lot of people think the or means and the and means or, right? They get them mixed up. And is for both things happening at the same time, or it means the first one or the second or both. Let's try another one of those weird ors. What's the probability of getting a club or face card? And the way I tend to do these is I write down how many of those there are. I write down how many of those there are. Then I take away the boths, right? So it would be the number of clubs plus the number of face cards, take away the number which are both. Okay, let's break this into little small chunks. How many clubs are there in a deck of cards?
13.
Okay. We've done face cards a lot, isn't there? 3, 6, 9, 12 of those. Now, they both might be a little bit harder to count, but you should be able to count them. How many cards are both clubs and face cards? Or another way to say that is face cards that are clubs. So how many of those are there?
3.
Now, when you put this package together, you end up with 22 out of 52, and then you simplify that down to 11 over 26. Are you comfortable now about how to do ORs? How many in the first thing, plus how many events in the second thing, take away the boths. The ORs are, the ands are a little bit easier, aren't they? Because ands are basically this guy, right? The both. Oops. Are we good so far? Let's look at some homework questions. Take that off. If I look a little bit distracted, I have got a dog fight under my feet. I'm just watching that they don't decide that my feet are part of the fighting. So if you hear a sudden shout, it's because, ow, perfect timing, just to prove my point. Having no issues here. Okay, what the heck is this doing? Okay, there we go. I got some weird window that was getting in the way of what I wanted to do. There. Are you now looking at intro to probability? Right. We've done questions like this before, but let's just pick one. Is each of the following values a legitimate probability? And you say yes or no. And if you do know, you tell me why. Is 0.55 a probability? Could you get a number like that from a probability? Agreed. Nods. So the answer is just yes. So let's pick a no now. Would you agree this is a no? 1.20. And they give you some reasons. And that's the right one, isn't it? They cannot be bigger than 1, right? Well, a very simple question to start life off. Suppose that a city has this number of households and you randomly select 900 of them. What's the probability that your household is selected? Well, that's just the top number is how many divided by 126,000. So far, so good. Right. It is correct, but it probably won't be accepted by WebAssign because of one little thing. What's wrong?
Not simplified.
Yeah. So could we at least knock off a couple of zeros? Do you think it can simplify more? You've got a 9 and a 1260. Do you think you can do better?
Might be able to.
Right. And the answer, you can. And it ends up being 1 over 140. No, I did not do that in my head. Whoops. Got to be careful what buttons I hit here. What I did, I guess I can come back for a second, just show you, is I used the TI-84. And you might have forgotten about the little fraction trick for it, so here goes. If you take, can't remember what our number was, 9 divided by 1260, I think it was. Probably means an extra 0 there. Enter, math, fraction, go. No, it is 1 over 140, it was right the first time, right? So you just type in the thing and then you do a quick divide, then you hit math button, choice 1, and it makes your answer a fraction. Right. A car dealer noticed that 4 out of 25 new cars ended up coming back within the first month for warranty work. And it says, write a sentence expressing this information using a proportion. Write a sentence using this information as a percentage, and then write it as a probability. Let's do this one first. So 25, 4 out of 25, 16%. Yeah. 4 divided by 25 turned out in percentage. If you want it as a probability and you want to do it as a fraction, wouldn't you use that one? Now, what about question A? Because in a way it's kind of silly. What's the answer to question A? You're thinking too hard. Or you're too shy to tell me. 4 out of 25 people? 4 out of 25 cars? Okay. That's all they wanted. Yeah. I made that question harder than it really was. So that's my fault. Right, so question 4, explain the interpretation of probability. Is it done through relative or personal? Right, according to Krantz, which is actually a survey, the probability of a randomly selected American being injured by lightning in any given year is 1 out of about 685,000. So if you never knew that, the chances of you, Walton, being struck by lightning are pretty slim, right? And the, oops, I probably clicked on that. Let's just click on anybody, get out of the way. Would you agree that this data that was collected would probably have been collected through relative frequencies? In other words, there's 300 million Americans, and they found out how many ended up in hospital because they were struck by lightning, and that's where that fraction came from, right? They simplified it down. That would be a relative frequency one. Now, according to my neighbour, the probability that tomato plant she planted last month will actually survive is about 1/3. What do you think about that one? Personal or relative frequency? I think the first 3 words tell me.
Personal, I think.
Yeah, I think personal. I don't think that person has done a scientific analysis over the last 20 years and found, lots of tomato plants. That would be my best guess. So here's another ones where they talk about personal against relative frequency. Here is a theoretical one then. Casino games often use a fair dice that has 6 sides, 1 to 6 dots on them. When the die is tossed or rolled, each of the 6 sides is equally likely to come on top. Using the physical assumption that the dice is fair, determine the probability of each of these. That you get 5 dots. I would probably phrase that as you rolled the dice and you got a 5. And would you agree that's 1/6? What about a 1 or a 6? Remember the or.
Be 2 1/6 or
Yeah.
1/3.
Correct. 2 6. Should simplify to 1/3. That's better. Let's get to that. An odd number. I guess we have to just check that, but 3 out of 6. Yeah, 3 out of 6. And that would turn into a half. Now, in that story, nobody, did an experiment and rolled the dice 1,000,000 times and found out how many were 6s and 1s and 3s. And then we just do it theoretically. We assumed that any number is possible. Just like I've been doing today, a lot of the questions weren't they all to do with card games. And it's time for us to say bye-bye. So